Good afternoon. In this video, I'm going to continue our discussion on the topic techniques of integration. I'm going to discuss in particular the fourth technique of integration, which is integration of rational functions by partial fractions. If you still recall, for the past few weeks, we discussed the following techniques of integration. The integration by parts, okay, the trigonometric integrals, trigonometric substitution, and integration of rational functions by partial fraction. This is what we're going to discuss today. Okay, so what we're going to do here is to discuss another technique of integrating rational function. In fact, this technique can be used to integrate practically any rational function. No? When we say rational function, that's the ratio of polynomials. And how do we do that? By expressing those rational functions as a sum of simpler fraction, which we call as partial fraction. Those simpler fractions are those that we are already familiar with, and we know already how to integrate them. So far, in our discussion, we talk about, I think, three formulas that deals with integral of rational functions. These are the integral of 1 over u du, okay, which has the integral ln of the absolute value of u plus c. The other one is the integral of 1 over squared of a squared minus x squared dx, which is the arc sine of x over a plus c. And then we have integral of 1 over a squared plus x squared dx, which is equal to 1 over a arctangent of x over a plus c. But there are rational functions whose integral cannot be obtained by using this formula. So we're going to discuss today another technique. Okay. First, I need to emphasize here that this method works only if we know how to express a rational function of the form r of x over q of x as a sum of partial fractions. To do that, we consider four cases, at least four cases of this idea. The first case is when your denominator, your q of x there, okay, is a product of distinct linear factors. So if your denominator is a product of distinct linear factors, say q of x, which is your denominator, is equal to the product of these are linear factors. No? You can express your rational function or of x over q of x as the sum of partial fractions, and those partial fractions have denominators which are respectively the factors of your q of x. And assuming that they are linear, then you will have this form. These are what you call as partial fractions. Okay, that's the first case. The second case is, although the factors of q of x are linear, but if, for example, there is a particular linear factor which is repeated, okay, let's say repeated r times, so that you can of course express that in this form, no? Then the rational function r of x over q of x can be written as a1 over a1x plus b1, assuming that this is the repeated factor, okay, plus a2 over a1x plus b1 squared, okay, and so on and so forth, depending on how many times is that linear factor being repeated. Okay, so that's for the second case. The third case is when one of the factors of your q of x, your denominator, is an irreducible quadratic factor. So if you have an irreducible quadratic factor, in particular, as long as this condition is satisfied, okay, your b squared minus 4ac is less than 0. I think this was included as a restriction, no? Because if you have any other case, no, let's say that this is greater than or equal to 0, then it's possible for your q of x to be factored, I think, over rational. Okay, so let's just assume that your quadratic factor is irreducible, then you can write the partial fraction as ax plus b. The principle actually here is if your denominator is quadratic, irreducible factor, then your numerator is not just a constant but a linear form, which is ax plus b. Correspondingly, from our first case, if you have a linear denominator, then your numerator is a constant. Okay, so that's for the third case. And the fourth case, of course, is you have an irreducible quadratic factor, and that quadratic factor is repeated. Okay, so again, you have your partial fractions in this form, depending on how many times is that irreducible quadratic factor repeated.